Hello, everyone, and a very warm welcome to Cognito's Key. I'm so glad you could join me today. We're going to jump right into the world of power electronics to uncover the secrets of these tiny, lightning-fast guardians that protect our most valuable devices from, well, electrical disaster.
So, have you ever stopped to think about it? All around us, right now, massive amounts of electrical current are flowing, powering literally everything. But what happens when that immense power goes a little wild? What's the one thing that actually stands between a stable system and a complete, catastrophic failure?
All right, let's get into it. The first thing we really need to wrap our heads around is just the sheer scale of the problem we're dealing with. You see, modern power systems aren't handling little trickles of electricity. No, we are talking about incredibly large currents. Now, when everything's running smoothly, that's fantastic. It's what powers our entire world. But if something goes wrong, say a short circuit, that huge flow of current instantly becomes incredibly dangerous. It can fry equipment, spark fires, and cause massive outages. So being able to cut that power safely and instantly is absolutely crucial. This brings us to our first line of defense. It's a device that's been the cornerstone of electrical safety for, well, a very long time. So at its core, any circuit breaker really has one main job: to stop the flow of current the second it gets dangerously high. You can think of it like a super smart automatic safety switch. It lets the electricity flow just fine during normal operation, but the very moment it senses a problem, its only mission is to break that circuit and stop the current in its tracks. But here's the thing about mechanical switches. They've got their limits. They have physical, moving parts. And what do moving parts do? Well, they wear out, they break down, and there's a limit to just how fast they can possibly react. In today's world of super-sensitive electronics, we need something much, much faster. And that's where the solid-state solution comes into play. And here it is, the hero of our story today, the static circuit breaker. The key words you need to remember are semiconductor, quickness, and reliability. You see, unlike its old-school mechanical cousins, this device uses powerful electronics, things like thyristors, to control the current. So what's with the name static anyway? Why call it that? Well, it's actually pretty simple. It means it has absolutely no moving parts. There are no physical levers flipping or switches being thrown around. Instead, it relies on semiconductor devices that can turn on and off at unbelievable speeds. We're talking microseconds. Just to give you a sense of how fast that is, a single microsecond is to 1 second what 1 second is to about 11.5 days. Wow. This lack of movement makes them not just crazy fast, but also way more reliable in the long run. Okay, but not all electricity is created equal. These static breakers have to deal with two completely different kinds of current. You've got alternating current, or AC, and then you have direct current, or DC. And the strategy for shutting each one down is totally different. And this right here, this is the heart of the challenge. You see, AC current is like a wave. It naturally goes up and down, and its voltage crosses zero many times every second. This gives the circuit breaker a perfect, natural little window of opportunity to jump in and act. But DC? Nope. It's like a straight, constant river. It just flows and flows in one direction, which means it never gives you that easy 0 point. So you have to literally force it to stop. For AC breakers, the solution is really quite elegant. The thyristor, which is acting as our switch, needs a tiny little electrical signal, called a gate pulse, to let the current flow for each cycle. So, to stop everything, the breaker's control circuit just stops sending the pulse. Simple as that. But it's not perfectly instant. As you can see here, when that turn-off command comes in, the thyristor that's already on will actually finish its current half cycle. But once the current naturally drops to zero, the thyristor won't get a new pulse, so it just stays off. And voila, the circuit is broken. So the main thing to remember here is that there's this tiny but totally predictable delay of at most 1 half cycle. But what about our stubborn DC current? Since it never goes to zero on its own, we can't just sit around and wait. We need a much more active, much more clever way to shut it down. And this technique has a pretty cool name. It's called forced commutation. Okay, this part is really cool. Let's walk through how this clever little trick works. First, the main switch, our thyristor, is on, and current is flowing normally. At the same time, a capacitor in a side circuit is charging up, kind of like a tiny little battery.
Now, when a fault is detected, a second auxiliary thyristor is turned on, and this is the magic step. It connects that charged capacitor across the main thyristor, but in reverse. And that jolt of reverse voltage is what forces the main thyristor to shut down, instantly cutting off the flow of DC current. It's just a brilliant bit of electronic engineering. So, after all of that technical stuff, why does this matter so much in our lives? Well, it's because these little devices are working silently all around us, every single day, keeping us safe.
And this quote, it really just sums it all up, doesn't it? In a world that runs on electricity, being able to safely stop a current isn't just a nice to have, it is an absolute must. And for our most delicate and important systems, static circuit breakers are the specially designed tools that get the job done.
So when you put it all together, it's that incredible speed, that rock-solid reliability that makes these static breakers so essential for protecting all the complex electronics that define our modern world. We're talking about everything from the data centers that run the internet to life-saving medical gear to renewable energy systems. They really are the unseen guardians, reacting in microseconds to stop a disaster before it even begins. And there you have it, the fascinating story of the static circuit breaker. Thank you so much for joining me for this explainer. If you learned something new today and found this interesting, please do me a favor and hit that like button, share it with someone you know who's curious, and of course, subscribe for more knowledge keys just like this one. Until next time,